is an example of a question that looks like it's going to be really difficult just because there are a lot of peaks in the spectrum. But as we'll see, it's actually really not that hard because you're already given part of the answer. So you've been told what part of the structure of the ibuprofen molecule looks like. And we've just got to work out what this part is, the R group. The rest of it, we already know what it is, and that makes the problem really quite manageable. So that's the essential information we've got, and what we're going to do is simply start by looking at the bit of structure we're given and see if we can identify the peaks that correspond to that part of the structure, and then we just take them out of the equation and see what we're left with that's left to account for. So we'll start with this. You can see at that left-hand end that you've got two methyl groups bonded to the same carbon, and therefore they will be equivalent to each other. So let's just look for the peak that corresponds to the 6 hydrogens on those methyl groups. And obviously that's really easy to find because there is only one peak with an area of 6, so it's kind of got to be that one. But we just need to double check, and in an exam you ought to do this and make sure that everything is accounted for. So it's got to be that peak at about 0.8 ppm because it's got the right area, but you can see it's also got the right splitting because next door to it is that CH that they're both bonded to. So there's just one hydrogen there, and so the peak should be a doublet, which it is. And the shift, well, it's just bonded to another CH, so that's an HCr shift, 0.5 to 2 ppm, which again fits. So that's the right peak. And so what we can do now is just tick it off. So mark it on the spectrum to say, right, we've accounted for that peak, so we're not going to think about that one anymore. So now let's start moving through the structure. We know that that CH must be there because it caused the doublet splitting. And so we should go looking for that CH. So the area has got to be 1. And you can see this time there are 3 peaks with an area of 1, so it's not so immediately obvious. But when we look at the shift, again, it's just going to be an HCr shift because it's just got CHs around it. So it should be between 0.5 and 2. And that suggests that is going to be this peak here. But we can confirm that by the fact that it's got complex splitting, and that's what we expect because it's going to be split by the 2 methyl groups there and by the CH2 here. So there's going to be a lot of splitting there, and that's consistent with this peak down here, which you can see has a large number of sub peaks there. So that fits the bill completely, and so once again we can say, right, that one's accounted for. So there we are. Now we've got 2 peaks taken out of the reckoning because they're already accounted for. Now we'll just progress on to the next part of the structure that we know. So next door there's a CH2, so it's going to be a peak with an area of 2, and there is actually only one of those, so it ought to be that peak at about 2.5 ppm. But again, we'll check everything. Has it got the right shift? Well, this time it's next door to a benzene ring, and that gives you a characteristic shift between 2 and 3 ppm. So yes, that fits, and it should be a doublet because you've got the adjacent CH on this carbon up here to the left, and there's no hydrogen, remember, on this carbon on the benzene ring. So just one adjacent CH, so it should be a doublet. So again, that all fits. So again, we have a peak assigned, and there it is. So those 3 peaks are now taken out of the reckoning. They're accounted for by the bit of structure we already know. And of course, there's one more bit of structure which we've also been given, which is the benzene ring. Now remember, when a benzene ring has two groups attached to it, as this one does, because it has the side chain that we've just worked our way through, and at the other side it has the R group. So that just leaves 4 hydrogens attached to the ring. So we should get a cluster of peaks with a total area of 4 in that aromatic region between about 6.5 and 8 ppm. And you can see that indeed we have that. So that accounts for that little cluster of peaks there, because they've got the right aromatic proton shift and the total area is 4. Remember, you don't have to talk about splitting for aromatic protons. That is stated in the specification, so they won't expect you to talk about those. Okay, so now we've accounted for all of the bits of structure we know about, and what's left is the mystery R group. But you can see by having taken out those 4 peaks that actually only now have 3 peaks left to account for, and that's a much more tractable problem. So if we add up the MR for the bit that we've now assigned, for the bit that we were given, it adds up to 133. And if we subtract that from the total MR, which we were told in the question was 206, then you can see that the R group should have an MR of 73. And that's obviously going to be important information when we start trying to figure out what it is. So we've got 3 peaks left, and you can see I've labelled them A, B, and C. So let's begin with peak A. So if we look at it, it has an area of 1, so we know it has 1 hydrogen only contributing to it. And that chemical shift is very characteristic. It's down there between 11 and 12 ppm. That's almost certainly going to be a carboxylic acid proton. So at this point, that makes us very confident that we have a COOH group. And OHs, remember, including COOHs, don't split, so it should be a singlet, which indeed it is. So that all fits. So it seems very likely that we have a COOH group in the structure. Okay, so we just note down that we have a COOH, which you're going to need to build into our structure. And then we'll move on and look at the next peak. So let's move on to peak C. So C, as you can see, has an area of 3. So 3 equivalent protons means it's likely to be a methyl group. It's a doublet, and that means that it must be next to a CH, a carbon with just 1 hydrogen attached. And the shift is about 1.5 ppm, so it's in that HCR region. So using that information, we can deduce that we have this in the structure. CH3 group accounted for peak C, bonded to a CH, and because carbon has to have 4 bonds, there must be 2 other things attached to that CH. And we now just have 1 peak left to account for. Of course, that peak must be the one that comes from this CH, because it's got to appear somewhere in the spectrum. So the peak we're talking about is peak B, and we can say, right, that is causing that CH. So again, we just need to check that that fits the appearance of the peak in the spectrum. So we're talking about peak B there. So area is right. It's got an area of 1 because there's just 1 hydrogen there, so that fits with it being that CH. It's a quadruplet, which means 3 hydrogens on an adjacent carbon, and again that's consistent with it being next to the CH3 there. So that all fits. Chemical shift wise, well, we've got two possible reasons why that chemical shift is in that sort of 2 to 3 ppm region, which is that we know we've got a benzene ring in the structure, so it could be adjacency to that, but we also know, of course, that we've got a carboxylic acid group. So there's our assignment of peak B, and we've just got to decide what connects onto those two bonds. So it seems likely, because we know we've got a COOH that we've got to build into the structure, that one of those bonds is going to be connected to the COOH. So let's put that in there and say, right, that's our PK assignment, is that COOH there. So we're going to suggest that this is a fragment of the structure. And we have no more peaks left to assign. So it could be that this is the whole R group, but we need to check before we just attach that onto the rest of the molecule that it has the right mass. So if you add up the MR of that group of atoms, it comes to 73. And as we worked out earlier on, that's exactly what the mass of the R group needed to be. So it looks like that's the whole thing now accounted for. So we have that group, and we have the bit of the structure that we were already given, and all we have to do is join them together, and we get the entire ibuprofen structure, which looks like that, and that's job done. So that question looked like it was going to be really quite tough because it was complicated looking spectrum, but you just have to read the question carefully, realize that they've got you more than halfway to the answer really, and so actually it wasn't that difficult, but you just have to keep your head and make sure you do things like keeping track of where you've got to by ticking off the peaks you've already assigned and that kind of thing, and that way it helps you stay focused and not get overwhelmed by the amount of data.